Okay, welcome to the final day of the Poly teaching week. I just want to start by acknowledging Sophie for all her amazing work, not only with the camera, but also coming up with exercises and a lot of behind-the-scenes stuff that makes things flow well. So yeah, thanks, Sophie. Okay, all right, so we want to talk about monads more, and then we'll talk about comonoids, and then that'll be the end of the thing. We'll talk about bicomodules a bit, polynomials in multiple variables, like Joachim was talking about yesterday, and then see what else there is to say. Okay, so yesterday we talked about how list was a monad, but Lott is also a monad. Lott, if you remember, has lots of positions, and that's a pun I didn't mean to make. P is a probability distribution on n. The reason that it's written delta n is the convex hull of n points. What it is it's the set of all p that goes from n to 0, 1, such that 1 is p of 1 plus p of n. Okay, and you can draw p. You can draw delta 0, delta 1 as a dot, because there's only one thing that works like that. The only one that would work is if p of 1 was 1. And delta 2 is like a whole line segment. For any number between 0 and 1, you can put that amount of probability on the first thing and the rest on the other one. And delta 3 is actually the thing that looks like a triangle. There's 3 numbers that add up to 1. Okay. So those are the positions, and for every position, the directions are just there's n and many, and it's like which ticket is chosen. Okay, so we've gone through that, and the point is that Lott is a monad. The point we're making today is that Lott is a monad. So if you have a lottery, so this one's like, okay, I have an M and a P, and I have an N and a Q. And I need to go to a lottery. But what is the type of M I'm indicating here? I would like to be able to write this as the on positions, as what a position in here is, but it's a little bit confusing if you're not careful. So what is the type of M? M is a natural. What's the type of P? P is a type delta M. What's the type of N? N is not the naturals. So what's happening here is that there's a pi. There's a...
Oh, does it take in the M?
Yeah. It's a map from M, which I guess I'm supposed to underline, to the naturals. So I'm not allowed to write a bare n and get a natural. I have to write n of little m to get a natural. Does everyone, can you read that? Because this thing is a choice of M, a choice of probability distribution on that M, and then for all n in M, M in M, a choice of natural, and a choice of probability distribution on it, y to the n. Yeah. Okay, does that make sense? So if I notate in here, whenever I want to notate something, an element of a sigma pi, sigma pi, sigma pi, it's as though you should always end it in 1 and put, like if you had a set here, just put it, what am I saying? That's not quite true. For sets, the way I notate one of these is every time I see a sigma, I write that. And every time I take a pi, I ignore it in my notation. But I know that the next thing is a function of that one. So on positions mean applies 1. And so to give a position of this thing, every time you see a sigma, write it, and every time you see a pi, know that that's an index. Okay, so can you read this? This is a lottery, and for every ticket, it's a lottery. This one's which one's not?
The one right lower your, yeah, that.
Is not a tuple?
Yeah.
Well, it's a tuple, but it's just that n has a type that's kind of fancy. N's type is written there.
Your first one is 2 tuples.
Oh, it's 2 tuples? Yeah. I mean, that's some kind of associativity that's not a big deal to me, at least. Is that okay?
Yeah.
Okay. Okay, and Q is of type?
Delta M2 delta M.
Yeah, it's of type M,
Delta.
arrow, del. Oh, wow, okay. Q is of type for all, okay, this is equal to the type for all M in M, N. Agreed?
Yeah.
This is of the type for all M in M, delta N M. For every number between 1 and M,
Okay.
this one gets a distribution on NM many tickets. So maybe we should give an example of one of, you have a question? Should we give an example of something in here?
So I am like
Lost?
totally lost.
Totally lost.
So maybe you could help me understand. So you said N is a map from the SAG 1 to M to natural numbers, but up above N in lottery is declared to be
A natural?
a natural.
Yeah, but I have, so what I rewrote Lott compose Lott
Yeah.
here.
Yeah.
And so we have,
Yeah. Okay.
so remember,
Sure,
an arbitrary polynomial P
Yep.
is the sum over I in P1
Yep.
of y to the something, but if I wanted to, I could write D in P
Yes,
bracket
that's right.
I,
Yep.
y.
Yep.
And then when I'm preparing
right.
to compose, I
That's right.
pop it right in. Okay. So now I'm just writing Lott, which I told you was this. I rewrote it.
Yeah.
I used M instead of N because I wanted to, yeah.
Oh, a thing of beauty.
Is it? Something's beautiful? Okay, great. Okay. Then I guess we're done here.
Okay. So.
But
so
whenever we see a sigma, we
Yeah.
put a little, we notate, to give a term of this type,
Yep.
this is not a type, this is a polynomial. If I want to plug in 1
Yeah.
because I want the positions,
Yeah.
then a term of this type
Yep.
will, what you do is I notate it like this. Every time I see a sigma, I put the
Yep.
notation, the variable name there with a comma.
Yeah.
And then I just keep doing that. Every
Yes.
time I see a pi, I know in my mind
Yes.
that I'm going to skip it, but that this next thing depends on it.
And
N
hence
is a
that-
function that takes in M as a variable.
And so that's why you had that nice little function.
That's why I had that nice little function there. Yeah,
Can you go over the types of the terms again?
they're here.
No, on the 4-tuple.
But they are the, I mean,
Yeah, no, just M is a net. Yes, M. Oh yeah, you did it above. Okay.
yeah, they're literally here. Yep.
Sorry.
Yeah, it's okay. This one, it's a little bit better to use pi notation because it's the one that that always works, whereas function notation works when it's when this thing is independent of M, right? If the natural is independent, all right. If the type of this one's independent of the choice here.
So if you
Sorry,
had
that was an aside. Okay.
if you had two pies, like let's say you had 5 pies
Yeah.
in there, instead of just one.
Yeah.
There, then N would be a function taking 5 arguments.
Yep. If we had 5 pies here, then the N would be a function taking 5 arguments. Yep.
And landing in the naturals.
And landing in whatever that type is there, which is naturals.
Yeah.
Yeah.
5 pies in a row, or
Yeah. Someone was asking. Yeah. Andre was asking I colon I product over J colon J of I product over K colon K of J
Yep.
sum over L colon L of K of 1, because we always kind of, if we're doing a set, I always like to end in 1 if, for the pattern to work best. And an element of this type would be I comma L. Oops, I comma L.
Yeah.
Where I is in I and L is in product over J colon J of I product over K and K of J LK. And so if someone wants to write an actual element of LK,
Yep.
they could write L of JK. Like they can,
L is like a tuple.
if somebody gave me a J in JI and they gave me a K in KJ, then I would be allowed to write this by like plugging, or maybe you'd prefer to write L of j k or something. Or a functional programmer might write L j k or something. Like function application, marching, yeah. Okay.
An element of that type would like open a lambda.
L is a lambda.
Yeah.
Yeah. And you can apply it to j, and then you can apply it to k, and you get out your, yeah. Okay. So Lott, it's, so moving into a, remember yesterday we were like, going from P to Q composed R composed S, blah, 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 is really easy. You say like for all positions here, a position here, and for every direction, a direction, sorry, I'll try it better. For every position in P, a position in Q. And for every direction there, position in R. And for every direction there, a position in S. And for every direction there, a direction in P. And so you kind of march through very cleanly. Here it's like given a position in Lott and for every direction another position in Lott. You kind of have to like put a bunch into a big sentence. It's not this kind of very procedural marching thing. Okay, so somebody gives us a lottery, and for every ticket of that lottery, they give us a new lottery. So I give you each a ticket. I have 16 tickets with different probabilities or whatever. I give you each a ticket. That ticket, you go up and look on this chart and you see, aha, my lottery is, and then you get this new lottery. You get a lottery with 16,000 tickets. You get a lottery with 1 ticket, etc. So that's what's going on here. Each of you has a ticket, and that ticket indicates a whole new lottery. Then from that, I can collapse into one big lottery. Okay? So monads are like collapsing. Lot moves to just Lott. They collapse things, and comonads are going to like be expanding and like moving out. Yeah.
Could you?
And we're trying to define this. We'd like to define this map, so soon we'll do that. Yeah.
You had this very nice way of saying, look, the case of this morphism down there with the compositions is a nice way to understand it with position, direction. This one, you said it's not like that because, and I'm just trying to calculate
mapping
that.
into a trie
Yes.
is easy,
Yep.
and mapping out of a trie is hard. I don't know how to say that. I do know how to say that. There's lots of ways to say that.
Got it.
But I'll
Okay, you said that.
I'll save that. I'll save that for a second. I'll say ways in which I can concretize or account for the fact that it's easy to map in and easy to map into a trie.
Okay.
Into a composite.
Thank you,
Okay.
thank you.
Okay. So, what are we going to do? I'm going to erase the right half of the board in 10 seconds, starting here.
Wait, right half of that board.
Yep.
Okay.
And because I want room to tell you what to do with this lottery.
So did we write?
In fact, I'm going to erase this too.
Did we write the unit already?
No, we haven't written the unit or the mu.
Yeah.
I was thinking of doing the mu first so you could tell which unit was the right one, but maybe you already know which unit's the right one. There's really, the unit is almost always the one you hope it is. So, I mean, but sometimes it's not. Because sometimes there are choices. Like for list is a monad, but it's also a times monoid, and so it can be confusing which thing that feels like it should be the unit is the unit for which. Okay, so we want to write down mu and eta, and we'll do that in a second. Yeah.
Have you thought about using like a Nelsonian notation for things like n there, where you put like n bar?
I have,
Okay, because
and I don't want
you don't like it. Okay, 'cause something to visually denote that it's a function I found really helpful in Nelson's.
I mean, every term of type, if n is a type,
Yeah.
and you have n in n, it's a function from 1 to n.
Yeah.
So everything,
Yeah. Okay.
It's already function E.
everything's already a function. Elements are functions. Okay. So I welcome you to do that if you want to do that. You'll have bars all over your screen. I find like extraneous things. Anyway, everyone has their own way that makes their mind happy, and that's, yeah, it's good to do the one that's good for you. Okay, so where are we going to take this thing? A lottery of lotteries goes to a lottery. Which lottery does it go to? Well, I need to give a natural number and a p. So what's the natural number? How many tickets are there total? You got 16,000. You got 1.
The multiplication of all of them? There's m.
And it's the sum of
No,
m
it's
plus
not
n.
M.
Or some, yeah.
Some what? How many tickets should we have at the end? So, okay, so I've got this lottery. This one is 0.3, this one's 0.3, this one's 0.4, this one's 0.3.
Is it this?
And in this thing, sorry, I know some people already know it, but now we have to go slower because not enough people knew the first time, which is fine. 0.5, 0.50, 0.25, 0.75, and this person gets a lottery with 0.3, 0.3, 0.3, 0.1. Okay, this is a picture of one of these guys.
Right.
How many directions are there in this thing, by the way? Because eventually we're going to need a direction. So how many directions are there in this thing?
9?
Yes, there are 9. Yeah. The directions are pick a direction of the first one, and then pick a direction of the one inside of it. So there, you could pick this one with this one with this one with this, 3, 4, 5, 6, 7, 8, 9. Great. Okay, what lottery should this go to? Well, there's a 30% chance that we got the 50-50-0 lottery, a 40% chance we got the 25-75 lottery, and a 30% chance that we got the 30-30-30 10% lottery. So what lottery do we get?
Chapman-Kolmogorov? Just
It's weighted sum?
yeah.
Yeah, it's weighted sum. It might also be called Chapman-Kolmogorov, but I don't know that term.
Oh, that's yeah.
Okay,
You know, that's how you compose.
so what's this one?
Probability.
0.15. 0.15. 0 chance of getting that ticket. 0.1. 0.1. 0.09. 0.09. Oops. 0.3. 0.09. 0.03. Okay, let's add them up. 30, 40, 50, 60, 70, 79, 88, 97, 100. Okay, great. Okay, and now for every ticket here, which is a direction, which ticket should it go to? On directions. We need to map back on directions. There are 9 tickets here. Where do they go?
The one it came
To the one it came from.
whence
Yeah.
it came.
Every monad that we're going to talk about, if T and U are Cartesian, these will all be Cartesian. What is a Cartesian map? Yesterday, Joachim defined it to be in terms of E and B. If you have a map of polynomials, it's one where you have a pullback, he said. But we don't think that way very much here. We don't think in terms of bundles. What we think in terms of is like maps on positions and maps on directions. And from that point of view, it's phi is Cartesian if for all positions in P, phi sharp I from P is a bijection. A one-to-one correspondence. He kept saying the fibers here are the same as the fibers here, and what he called fibers are directions, or the fibers are isomorphic, and that's what we would say too. So what I'm telling you is that all the monads, most people only care about, and there are interesting monads that are not Cartesian, like for gluing in sheaves. If you have a sheaf, you'll get a non-Cartesian monad. But most people throughout the history of polynomial functor research have focused on monads, and they focused on Cartesian monads. Most people care about Cartesian monads. And all of ours are. And all of ours are.
So that's the
By all of ours, what I mean is all 7 of those are. All 7. Someone say something?
That's a different distinction than like finitary versus non.
Yeah, it's a different distinction than finitary versus non. This is about that the number of tickets here was the number of tickets here. 9 was 9.
Yeah.
Yeah. Okay.
I'm still kind of missing what the MP NQ maps to 1. What exactly is that? Is
Ouch.
the 1?
That was not a 1. That was an open paren. This was going to be this was going to be n1 plus dot 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 plus nm, comma, the appropriate distribution. I mean, I like, yeah. When the biggest problem I'm having is that I've been writing naturals, if this is my mistake, for ob fin set, when they're not the same. But I've been thinking of the naturals as objects of fin set, and it's just a kind of an abusive notation that I've let myself fall into. So every time I've been writing naturals, I've been thinking in my head I could put any finite set there, and that's fine. Like 5 means a 5-element set. But I told you no. I told you that 5 meant the 5-element set 1, 2, 3, 4, 5. It's always, yeah. So what I would write here is the sum over m in m of nm. But this would be an overloaded symbol. Am I talking about plus, like plus of numbers? 6 plus 3 is 9, or am I talking about disjoint union of sets? And if I was talking about disjoint union of sets, I'd be way happier, and I wouldn't need to underline stuff, and everybody would be, it'd be a better world. So in your mind, you could take naturals to mean ob fin set, and you might be happier. So now, another nice thing is I can actually take a pair, mn, in here, and tell you what probability it goes to. So what probability, if someone gives me an mn, they're actually pointing to a ticket. What probability does it have by Chapman-Kolmogorov / weighted sum? P of m times Q of n. So it's very easy to write down if you let yourself use finite sets instead of natural numbers. That's what we did on positions. And then on directions, given mn, I send it to mn. Any questions? Okay, what is the unit? To give a map from y to something is just to pick a position. Which position should we pick? In 1, yeah. Yeah, 1 is the thing that if we, there's a unique distribution of type delta 1, unique element of that thing, and it's the thing that works. Yeah, 100% chance. Questions about Lott?
So can you say the thing with the unit again? I'm not sure I caught that.
To give a map from poly y comma p is p of 1, right? By the Oneida lemma, or by the fact that it gives the position in every direction that goes to unique direction,
Yeah.
p of 1. So if somebody says, I need a map from y to Lott, they're asking you for a position.
Okay.
Which position of Lott should we give them for the unit? Well, 59.
Just like pick one basically, or
Okay, but it better be unity.
so you just pick the first position of the.
You pick the one that feels the most like unit. So is 59? Which natural number? Oh, yeah. Which natural number feels the most like unit?
1.
Right, that's the one that works.
Oh, so y to Lott, you pick the 1 element probability distribution with 100% chance of
Yep.
that 1 element.
Yep,
Okay.
yep. Eta of the unique thing is, maybe I'll write eta of exclamation point is 1, comma, the unique thing.
Okay. Yeah.
Okay. Yeah, our intuition for unit usually works well. It usually feels like the unit, like the thing that's most one-ish. That is, with list, you could ask, what's the thing that's most one-ish? The empty list or the one-element list? And it kind of depends, because list is like 1 plus y, and that's pretty one-ish. And one-element list is pretty one-ish. And so it's easy to get confused, and one is the unit for one and one is the unit for the other structure on list. Yeah.
Sorry, so maybe you could help me just do the type checking on that formula you wrote down, the one and the two there, the mu.
So nm is n applied to m, is that right?
Yeah, nm
Yeah.
means n applied to m. Yeah.
Okay, and now you're applying on the right there, mn maps to, yeah, great, nice. Maps to p of m times q of n.
Yep.
Where the
Those
the
are
times
numbers.
is monadic, is monoidal.
Which thing? Times is these are numbers between
Okay,
0 and
these are
1,
numbers.
and I'm multiplying those numbers
Okay, so p.
like
P-
this, right?
Yeah.
Yeah.
So p is of type delta m, and delta is a set of functions.
Set of probability distributions on n element set.
Yeah. Which are
Which are functions, sure.
right. So okay, each of which, but it's a set. So how can you apply it to m?
P is an element of a set
Is an element
of delta
okay,
n,
okay,
yeah.
Okay, and q is
An element of delta n.
okay. Q is a product.
Oh, oh, sorry. You're right. Thank you. This is bad. Q sub m
Okay.
of n.
Okay. Thank you.
Thank you. Good catch.
Sometimes writing it down
Yeah.
on the fly. helps
Okay.
you spot.
Questions? Someone have a question?
No, that makes sense. Yep.
Okay. So let's suppose that T and U are monads. And so T has its eta and its mu. And U is another monad which has its eta and its mu. And then someone tells you that TU is a monad, T times U. Someone comes and tells you, oh, TU is a monad. And you're like, oh, okay, what do I do? Well, what do you need to give to show it's a monad? You need to give a unit, and you need to give a multiplication. And you need to prove some properties, and we've been like ignoring that. You're supposed to believe, or say you don't believe, either one. Believe and go home and try it, or don't believe and say, I need more. That this is associative, that if these had ticket lotteries inside of them, and we consolidated first into these ones and then up here, versus like first consolidating here and then like bringing the little ones in, we would get the same answer. That's just the fact that probabilities work right. Hopefully you kind of believe that. Well, not hopefully. Hopefully you do what feels right to you. But that's a thing that you can check. And so we're going to write down why this is a monad. And I have not written down the proof that this is a monad. So really you should check this one. But I know I can write down the unit and multiplication easily enough. And it doesn't feel like I'm cheating when I do it. And I checked that I understood something else that I'll tell you about. And so I'm pretty confident it works. But I've been wrong before. And that happens enough that like you should probably check this if you want to like actually cite this. Or it's probably written up lots of different places, and everybody knows this except me. Okay, so now we need TU. And what else do we need? TU, compose TU to TU. Oh, is this the thing where? Yeah, okay, that should be fine. Okay, so how do you get the first one?
I mean, you're gonna have to do something with both units, so.
Yeah.
Because you promised me that they independently were monads,
Yeah.
can't I use the two?
How? How do I use it? What do I write here?
I think I want to write the the
Eta? Yeah.
um, the eta t and eta.
Like with the word and in there, or
I think with the triangle.
no?
No, time.
Closer to times. But times, if I have P1 to Q1 and P2 to Q2, then from there I get P1 times P2 to Q1 times Q2.
Yeah.
Times means a monoidal product. But you're almost right. What's your map from y to oh, to y squared? Yeah, that should work, yeah. Oh, okay. I guess you were right. But you're really implicitly using this isomorphism without notating it.
Wait,
And it's nicer.
y times y is y squared.
Yeah, it's not y squared. It's not an isomorphism. Okay, sorry. But it's still right. You're using this map without notating it. So I don't think it's right to say a to t. You should say like. So how do you notate a map? If I have a map from P to Q1 and P to Q2, how do I notate the map to P1 times Q2, Q1 times Q2, which, by the way, I just write with that. The way you notate the map here is usually people put it in commas. Phi1, comma, Phi2. Yeah, so this is eta t, comma, eta u. Yep. Does that make sense? The product of polynomials is their Cartesian product, is their categorical product. Yeah. Good?
I think so.
Okay. Okay. Everyone all right? Okay. Now we need this one. How do we get a map from TU, composed TU, to TU?
Oh.
That was just some timesy stuff. Sorry, Nate. That was just, yeah. How do we get this map?
Well, we could
Yeah.
seek to rearrange it.
Yeah, how do we
combine the T and T and the
Yeah.
few.
Does anyone remember what this is?
Yeah,
isomorphic
so
to?
you can use that distributive.
Yeah, distributive. Therefore, so it is.
Yeah, the duality.
No, it's not duality. Nope. Nope, it's a different distributive thing. It's that P1 times P2
Right.
composed Q
Yeah.
is
Yeah.
T
It's-
or T?
Is P1
Not ti- no-
Q, P1, yeah, Q, the P times P2, yeah.
yeah.
How come you wrote times in one, the upper one?
I don't know.
bottom one?
So I allow myself, okay, this is just me. For me, I can write this or this.
Yeah.
This is the tightest binding thing.
Yeah.
Like if I ever see like PQ plus R
Yeah.
S composed,
Yeah.
this one is P times Q.
Yeah.
And this is the loosest binding
Oh,
one.
wow.
Because since I have this,
Yeah.
this means, boy, you really don't want these bound. So that's what I do. I give myself both because this is high school. They did it in high school, so I'm allowed to do it. That's the rule I give myself. You can pick your own
Did you show
notation.
us that distributive rule before?
Yeah.
Okay. Is there a name for it?
This is like for any two functors, the product of functors is given by the product of,
The composition. Of the composition.
yeah.
Yeah.
Yeah, we did write this down before.
We did
yeah.
it for plus.
It was like one of the very
plus.
first things we did, yeah, when we did
We
composition.
said
yeah.
the world quaked when it turned out not to be true.
For tensor, oh yeah. Okay, so this one is T composed TU times U composed TU.
Wait, wouldn't it be T try U times T try
T try this thing. This thing is Q.
Oh, right.
Okay, and then what do you do?
You do it again?
No, we're, yeah?
Would this work if the try is on, like if the product is on?
No, this one is not true.
Yeah, okay. So that's why you can't do it again.
Is not, oh, I see, yeah. No, you can't do it. This is not, in general,
Yeah.
like y squared of, wait, what? Y plus 1, what, of 3 times 4 is not y plus 1 of 3 times y plus 1 of 4. Okay. Okay. So what do we do to use our monads?
You can swap the TU on the right-hand side to get UT.
I wish I just had t compose t, because then I'd be able to
Yes,
multiply.
exactly.
This is this u's in the way. But this is a product, t times u.
Yeah.
I can project.
We can project.
Wait,
Whoa.
what just happened?
Whoa.
This was like
I
t.
have it.
Oh.
Yeah, go ahead.
I have a T and a U, and I can just worry about one of them.
Yeah, there's a map from PQ to P.
Yeah.
Yep. I mean, so this is a product,
Yes.
so we can project. If you want to check it on positions and directions, given a position of P and a position of Q, we need a position of P.
Yeah.
Got it. Given a direction there, we need either a direction of P or a direction of Q. Got it. Okay, so that's the projection. And what we did is we just projected out the U there and projected out the T there. Or sorry, I say it wrong. Projected the T here and projected the U there.
Oh, right, yeah.
I usually say projected out to mean the one I'm leaving behind, which is bad.
I'm confused
Yeah.
though. Wouldn't we, I thought we were transforming it with isomorphisms
No, I just have to get from here to here. I just need a map.
Okay.
And
It can be lossy.
it can be lossy. Yep, it's lossy, yeah.
Well,
So
I'll be.
Can you write the what the right facing arrow is below? Yeah, that one
Times
is fine. So it's
mu
MT and
u.
U.
Okay, this one?
Yes.
If I had to notate, well, what do you want to call this? Do you want to call it pi 1 or something?
Yeah, yeah.
Okay, then I'll say this one is t trie pi 1 times u trie pi 2. Sometimes I like to call this thing like, well, yeah. Okay. Yeah. Okay. Okay. Questions?
So that map there that you wrote with the projection, what it's doing is look, what it's doing on either side of the projection is
Yeah, let's see. So I have this pair of a t thing and a position of t and a position in u, and then it's branching all the t times, and then it branches all the u times. Right? That's what tu is. A position would you call out a position of t and a position of u, and then a direction of t plus direction of u.
Yeah.
And then for each one of these, you have a pair of like I1, J1. And then you have this like branching part for T and branching part for U on each of them. If you were on the T side, toss the U. Throw it in the trash. Not going to use it. And if you're on the U side, toss the T.
so will you just
Toss the coordinate T and all of its directions.
so what you just described is the action of the map of this.
Yeah, I'm telling you how to compose a length 2 tree, a height 2 tree of
Right, but-
TUs. Yeah.
But what I'm asking is the action of this map. T.
Well, this map is along the way. I don't know. What does it do? This is the map where you're tossing. This is the throw away the U's on the T side
Yeah.
and throw away the T's on the U side.
Okay.
Yeah. And then the collapse is the last step.
Yeah. Right.
Yeah,
Okay.
yeah.
So that's
Now you're just going to have a T-ish thing here and a U-ish thing there, and you know how to collapse those trees.
So when you asked
Sound?
So,
Oh, this funny sound. Okay.
when you said if you're on the T side, throw out the U's. If you're on the U side, throw out the T's. That's the action of this map
Middle
with
step,
squiggly
yeah.
line.
Yeah.
And when you collapse it down, that's the action of n of mu t times.
See? Yeah, this is the action of ut times mu u. Yeah. That's the collapsing.
That's the collapsing, and the when you branch out, if you're here, toss the other thing. That's the
here.
action of this one.
Yeah.
Got
Yeah.
it.
Nate?
Yeah, so David, over here, this map where you took into account the distributive property has an equal sign.
It's always ISO.
Oh,
Sorry.
okay.
Yeah. Okay.
Oh, can I
Yeah.
ask another dumb question?
You can try.
Because I feel, David, that I've sinned.
Okay.
So that isomorphism map, I have,
Which one?
I will share with you. That isomorphism sign?
Yeah.
I've sometimes written it as a single line with a tilde over it.
Okay.
But is that bad?
That's what Joachim was doing yesterday. To me, in my life, I don't know. I thought this was equivalent or sorry.
congruence?
I don't know. I don't know what I think anymore.
Okay.
It doesn't matter to me. This is like some kind of equivalence relation, I think. This to me is like, I don't know.
Okay. So
I
won't
forget.
be defenestrated.
No. I don't know which one people like. Joachim seemed to like this one yesterday. I've been writing that one.
Okay.
I think this one's like semi-Q, so that feels less strong than Kong.
Yeah.
I don't know. Yeah.
If I'm
This
in
one
with
feels strong to
Joachim,
me.
I'm
Yeah, you're in good company.
What does the arrow represent when it's like kind of curly on the tail?
Like this?
I mean, that's not really an arrow, but yeah.
I go like this when I'm like indicating something,
Okay,
whereas I draw this when it's an actual arrow.
Yeah.
Yeah. I didn't even put an arrow. I was so, yeah. Okay. Okay, any other questions? Sorry.
Can we do another one of these?
Yeah, let's do another one. So maybe I erased something Nate liked. I hope not.
Well, I will take a photo just so you can erase with abandon. But
Oops. Okay. So let's do. We're definitely going to do number 7, but I like a fact a lot that, like when I saw this, I just thought this is just amazing. So I want to give you 2. Yeah. Okay. I'm not going to tell you that. What do you say? Yeah. I'm not going to tell you, except so let T be a monad. I'm going to give you 2. I will tell you. I'm going to give you 2 lax monoidal functors from poly up to poly. You can ignore what I just said. For any p comma q colon poly, we have t to the p times t to the q to t to the p composed q, and t to the p composed t to the q to t to the p times q. And these are lax monoidal structures. Meaning you can take the times and it turns into a trie, and take the trie and it turns into a times. Just crazy. I'm just so shocked about this. And this really uses those day convolution things. We could try to get these. Should we try to get these, or should we try to write this out?
Can you just state it again? Sorry, I was
Well, I just wrote it. So there's 2 facts. Like there's this lax monoidal functor like this that says like t to the p times t to the q goes to t to the p composed q, and t to the p composed t to the q goes to t to the p times q.
Those 2 are lax monoidal,
And each of these are lax monoidal.
and that has nothing to do with monad.
And t must be a monad for this to work.
Okay.
David, I'm going to ask a question of
Yeah.
outlandish stupidity.
Wow.
But T,
Everyone gather around. Here comes something really interesting. Yeah.
That's right. I'm gonna grunt.
Okay.
So T and U are monads, but
Yeah.
they are not polynomials.
Oh, sorry, polynomial monads.
Okay.
Sorry.
Okay, my grunting
Okay.
had
Yeah.
impact.
Okay.
They're,
Okay.
they're monoids in.
They're monoids in poly. Yeah. I mean, maybe this is true.
But they're,
Anyway,
they're polynomials.
This one's probably fine. Everything's probably fine, but I don't know for sure.
But they're polynomials.
Yeah, they're
So,
polynomials.
so David, how would that then, that one you just wrote there, the second one, yeah, that very one, if you had tensored those together, you'd also get t to the p times q, wouldn't you?
Because there's a map from t to the p tensor t to the q
Yeah.
to t to the p times q. Yeah,
Yeah.
that's true.
So,
Yep.
so that also gives you
A third one? Yeah.
on the right-hand
That's true.
side, yeah, a third one, t
Yep,
to the p
yep,
composed,
Yep.
t to the
Tensor.
q
Tensor. Yep.
goes to t to the p
Times q.
tensor
Times.
times.
Yeah. Yeah.
times.
But that has nothing to do with it being a monad. Like you don't need.
Yeah.
This part has nothing to do with being a monad, but then we could again go to t to the p times q.
Yeah.
Yeah. This one's also laxmonoidal.
Yep. Okay.
Okay.
Happy
Um,
to get it. Thank you.
Yeah. I don't know whether to do this or not. Does anyone have a vote? They're amazing to me, but I don't know if we should I don't know. I don't remember how it goes. I'm just assuming that it's going to work. I'm kind of flying by the seat of my pants to try it.
Well, what would you want to show? The laxmonoidal.
How it works using the day convolution stuff. Sophie?
I feel like I'm more excited about having more time on comonoids.
More time on comonoids. You're right. Okay, she's right. Thank you, Sophie. Okay, So, let's do one last thing, which is the free monad on P.
Oh, yeah.
Okay.
Okay, David, yes, you have free game for that. I think the center board is captured for posterity. Yes, it is.
Okay.
David. Oh,
Sorry. So,
Weight shifts very fast.
yeah.
So by the way, so I have a map from t to the p, composed t to the p, to t to the p times p, right? But I also have a map, because I have a map from p to p times p upstairs, I get a map like that downstairs, right? Since I have a map from p to p times p, and exponentiation is like contravariant, right? Then I get a map like that, and this is how you, if you use this one, you get the number 5 or whatever it was, that t to the p is a monad. And yeah,
Sorry. So the left arrow is the laxmonodality.
Yeah. Yep. And this one is t to the like pp, like t to the diagonal.
But it's going this way.
Yeah.
Oh yeah, but all directions, right?
No, not direct. This is so if I have p1 to p2, I get a map p1 to the q to p2 to the q, and I get a map from q to the p2 to q to the p1. Yeah. So if I have a map forward, then I get a map. It's exponentiation is contravariant in the
This is
exponent.
Like
And
exponential arrows.
yeah, exponential arrows. Yeah, maybe.
So you have, yeah, when you have f to the a. What it
Yeah.
means.
Yeah. Yeah. If I have a map a to b, then I get a map from x to the b to x to the a.
Yeah, exactly.
Yeah. Okay. So I want to do the free monad and then move on. Free, yeah.
Can you please just do the units like the
Unit?
map? Yeah.
Yeah.
Unit
T to the y is t composed y plus 1. And so the map from there goes to the unit and then the 1. Sorry, I don't know if this is helpful. But the other one would be y to the t to the 1. Well, t to the 1 is t. And so this is just the unit of t. So this one's the easy one. This one's the more surprising one in some sense.
Wait, I'm confused. You just showed the unit for the monad. For what monad?
For these two monads.
Oh, okay. But why did you point to the right when you said this one is more surprising?
I find this one a little bit more surprising. I don't know. They're both kind of surprising.
But they have
But
nothing to do
this
with-
one I just wrote really easily. This one I think I need a little bit more. But yeah, this one I need to use like day convolution-y stuff, like some of those fancy maps that I kept being like, I love these, but I don't want to tell you why. they're the ones that give you these.
Yeah, but again, they have nothing to do with, I mean, they depend on T being a monad,
Yeah.
but they're not part of a monad data.
Let's do a little bit more. I know we're all excited. We want to get to comonoids, and maybe this is, yeah. But let's keep going. So I want to go a little further. T to the A, I want you to come up with, on your paper, a map from T to the AY to the plus, T to the AY to the B times T to the BY to the C to TY to the T to the AY to the C. Yeah. Try to come up with a map like that. And then see if you can say the word Kleisli category of T in a way that, if you don't know what that is, maybe you don't know what that is. People don't know what that is. Okay, then, yeah, just do this then and see if it's, yeah. I just want to say this is, yeah, okay. Exercise 1 is find this. And exercise 2 is show there's an isomorphism. Give me an A, then run T, then spit out a B or halt. So T. Okay, let's see if we can do these things. Okay, let's do number 2 first. Does anyone know why T to the A, Y to the B? Can you calculate what that is? We did this the other day. We said that P to the Q, or Q to the P, we said, was the product over all I and P of 1 of Q composed Y plus P bracket I. So we can just plug and chug. This is product over all A in A. Those are the positions of this thing. Of T composed Y plus the directions there, B. But that's the same thing as Y to the A composed P. Maybe this one's harder to see. Do you see it? Y. This says for every A, give me the rest. Yeah. And so what is T A Y to the B of 0? Well, it's Y to the A composed T composed B. I don't know why. It's like you plug in 0 for Y here. You plug in 0 there, and you get what I just wrote. And this is a set. This is the set. I don't know why I'm having trouble like making this seem obvious to myself. It seems obvious, but I'm not sure anyone's going to follow but me. But the set of things here is for every A, for all A in A, a T of B. Maybe I just shouldn't have collapsed out the A or whatever. But this is functions from A to T of B. Now, people who know the Kleisli category know that this is a map in the Kleisli category from A to B. And so what I'm saying is that this is an enrichment of the Kleisli category. And this whole thing I'm telling you about in number 1 that we're about to write down is how composition in the Kleisli category works. It's just all about monads and their exponentials. But if you don't know that story, that's okay. You don't need to know that story. It's just a fact that what we're saying next is if you have Y to the A composed T composed Y plus B. So if you've got a machine that takes in an A, spits out a lottery that either returns to base somehow, like returns something like hello, or exception B, like stops with a B, So you've got this machine, takes in an A, runs a lottery, and either prints out a B or does something else that we're not sure of. And you've also got something that takes in a B, runs a lottery, and exceptions out with a C, or returns. I used to think if I ever hit a B, if I ever hit a constant, all machines stop and the whole world ends. But that's because I was living too much in tensor. If you live in times, something else can come along and pick it right up. Because that very first day we wrote that if you have y plus a times y to the a, you get to keep going, kind of. Because this thing is y to the a. And all we're writing here is eval. OK, so I don't have to write these big parentheses because I told you that the times symbol is the least binding always. OK. OK, so what we're writing now for number 1 over there would be how to turn this into something that takes in an A, runs a T, and then gives out a Y, or either returns or gives a C. OK. There's lots of ways to do this. One is to use those crazy day convolution-y things I told you, those different days, different times, and you can get this map. Another is to use only the structures on the board here, and that's a little bit nicer. So let's just do that. So we have t to the a, y to the b, times t to the b, y to the c. Does anyone know the first step?
Use the first.
Yeah, use the first thing to get t to the a, y to the b composed b, y to the c using this one. And then we wish we just knew some map to t, a, y to the c so we could be done. But how do you get that? Well, if this is going to be like boilerplate, if this is going to be as simple as possible, we want it to be because it's t to the something. We want to use this fact, that exponentiation is contravariant. Meaning if you have a map from P1 to P2, and any q in poly, then you get a map from q to the P2 to q to the P1. So we want question mark to come from, so we have a question mark to t to the a, y to the c, and that thing, it's enough to question, can you give me a map from a, y to the c to a, y to the b, composed b, y to the c? OK. So to give a map into a trie is easy. For every position here, so for every element of A, I need an element of A. What do I pick? Same element. And then given a B, I need an element of B. Same element. And then given a C, I somehow need to find an element of C. I'm allowed to use the A and the B I already had. What do I choose? C. Yeah. So this is a very easy map. And now we are done. If I want something, I put a question mark, and then I deduce new question marks until the bottom, and I put a check when I'm done. And then it goes up. The deduction goes up. Any questions on this? So if you care about Kleisli categories, if you care about like monads and how they're used in functional programming, you care about like maps from A to T of B and maps from B to T of C. And those feel like somebody had to create them, or, I mean, really not. They're the initial object in the category of all adjunctions that give you a monad, blah, blah, blah. OK, they're very special things, but they also come to us for free from this kind of calculation. Any questions? This is some kind of enrichment. This sort of thing is an enrichment of the Kleisli category in Poly. It's a lifting of the Kleisli category to Poly. Yeah. Questions? OK, I think we need to do the free monad, and then and then we'll try to go on maybe some kind of break or something, and then comonoids in Poly, which are categories. Okay, so yesterday, Joachim said that for any, so I'm going to write M sub p is the free monad on P. So if you have any polynomial, the free monad on it is MP. This is just notation. I write math frac M. What does that mean? If you like adjunctions, then what you would say is you have poly, you have monad, you have polymonad, and every polynomial monad, like T, eta, mu, you can take its carrier, which is just T, and that has a left adjoint, M. And that's what it means that it's the free monad. But if you don't know it, so basically, if T is a monad, then you'll get a map from MT. You'll get a monad map from MT to T. M is like a monad, and if T already, no matter what P is, MP is a monad, and if P already was a monad, if it was T, then there would be a monad map that was kind of universal. So we'll explain how M is this way of freely making monads. Yeah.
Yeah, so David, I'm
You're
struggling
back here?
with
Yeah.
this item that we're using here, and I'm trying to remember. Yeah, it's the first one up. The essence of my question relates to the first one, the one we're employing here. So that term on the left of the arrow there.
Yeah.
Because of symmetry of times, we could flip the.
True. Yeah.
But there's no symmetry in
Yeah.
the exponent to the
Yeah.
right.
That's right.
P
Yeah.
P try
Yeah.
Q is very different from Q
Yeah.
try P.
Yeah.
But somehow,
Yeah. You're worried that this is symmetric, but this one's not symmetric.
exactly.
But were you worried yesterday that we had this?
Yeah, right, okay.
Yeah.
Fair enough. So
It can happen. Yeah.
it can happen.
And so you're saying, well, this is isomorphic to Q
Yeah.
tensor P,
Yeah,
and that goes to Q try P.
yes, exactly.
And so I have a map to both of them.
Yes,
And then the person says, well, cool, that's good, not bad.
yeah.
And like you're not confused which map you are, which map is
That's
which.
right. Yeah,
Um,
okay.
I
So-
guess the only time you could be confused is if these were both P's. P to P try P versus switch and go to P to P try P.
Right,
Do you get the same thing or not?
right,
I feel like you probably don't, but
right.
I don't know. That would be the confusing moment. So if you wanted to go investigate, that's what I would look into. Usually mathematicians are like, is there anything about this that's going to be confusing? If so, I hope that it agrees. And if not, I want to note in my mind that this doesn't agree. So it would be nice if I already knew the answer,
Right.
but I don't remember the answer.
Okay, so what's weird about it
Yeah.
is that you have a map from P tensor Q. Oh yeah, you have a map from P tensor Q to both P try Q and Q try P.
Yep, I sure do. And they're not the same because these aren't the same.
Yeah.
And so it's pretty unlikely that if P happened to be Q, that I'd just get the same map. It just seems very unlikely because they could be different. So it seems very, very unlikely. So I'm going to like conjecture that these are not the same map even if P equals Q, and these are not the same map even if P equals Q. Yeah. Okay. All right. Free monad. Okay. So yesterday, did he? I forget if Joachim said how to get it, but yeah, I think he just said it satisfies this equation. And it's the least thing that does. But I want to tell you how to build it. He also talked about W types, and he said the W type for P is, I would say it's M sub P. He said it's MP plus 1 of 0 or MP of 1. He didn't write it in those terms, but that's the sort of thing he was talking about yesterday in the colloquium.
What do
Okay.
you mean the W type
That's
is this
set, which happens to be also this set, the one I erased. Okay, so that's the sort of thing he was talking about yesterday, because the free algebra on a set is given by taking the free monad and applying it to 0. But anyway, he was interested in W types, but we'll be interested in something more, which is like the free monad itself. And so I want to tell you how to build the free monad. The free monad, when P is finitary, is easier. If you want the full story, it's not much harder. But I don't want to go into it because I wanted to get into comonoids. So I'll tell you what to do if P is finitary. Finitary means that all the exponents are finite sets. So list is fine, Lott is fine, y cubed is fine, but why the naturals would not fit here? Okay, because the naturals is not finite. There still is a free monad, I'm just not telling it to you today.
Wait, list is fine?
List is fine because it's finitary. Finitary means all the exponents for all I in P1, P bracket I is finite.
So it's like an infinite number of.
You're allowed to have any number of coproducts. You're allowed to have any number of summands, but each one of them has a finite number of directions. Okay. Okay, let P0 be y, and let Pi plus 1 be y plus P composed Pi. Maybe I shouldn't be doing this. Maybe I shouldn't be doing this, but I'm going to do it. I think I'm going to do it. So I have P0 to, does anyone see a map from P0 to P1? What is P1? What is P of 1? Y plus P. Try y. Okay, do you see a map from P of 0 to P of 1? From y to y plus P? Well, there is the inclusion of the unit. So this is y, and this is y plus P, and we just do, yeah, we just include the unit, y to y plus P. And then, maybe this is a bad, oh well, I'm in it, I guess. Given Pi to Pi plus 1, like the one we just have, we get Pi plus 1, which is y plus P composed. So if this is phi 0, and this is, we have now phi I, and we have y plus Pi, we need a map to y plus P composed Pi plus 1, because that's Pi plus 2. Any guesses on how to get this map? Someone gives us a map from Pi to Pi plus 1, and our job is to get a map from Pi plus 1 to Pi plus 2 to do an induction. And what that means is, by definition, we need a map from y plus P composed Pi to y plus P composed Pi plus 1. And we use y plus P composed phi I. We just take the old one here, and we just like use monoidal products to get the rest. I feel like this is too much. It's written somewhere else. We'll have it written. Sophie and I are writing something about this, and it'll be online soonish. And I just want to tell you what these trees, what MP looks like, because I think that'll be easier. What MP looks like is either a caret, like a single little thing just sitting there, or a P-shaped thing, so something in P1, and then for every leaf, you can choose a caret or another P-shaped thing.
Carrots and peas.
Peas and carrots. So if P was like y cubed plus y squared, and that's it, then what I'm saying is to draw an object in here, a position in here, you either put a y or you put a p, either a y corolla with 3 things or a corolla with 2 things. And then on all the open leaves, you put either a y or a corolla with 3 things or a corolla with 2 things. And you keep going as long as you want, but you eventually stop. And you have to eventually just hit everything with a caret. Everything's got a caret.
So this is what position?
A position in this, the positions in this are all possible trees you can write that way.
Okay. Okay. And
Nate?
what's the,
And well, let's say what the directions are. What do you think the directions of this tree are?
wait, sorry, would you mean with the y with just a caret? Is that just like a
Oh, I said that it's like y, sorry. I said it's either y, a position in here is either like a position in here or a position in here, right?
Yeah.
So it's either a position that I'm going to draw with like a little caret, like the head of an arrow,
Yeah. But why
Or-
is it just an arrow? Just a single arrow?
if you want, but then your trees will have length different than. Now all the trees have length, have max height, the number I wrote there, have height that number. I guess I just wanted that, yeah. I think that, I don't know, maybe it's, maybe there's other ways to do it. You can put an arrow if you want. Okay, yeah.
I'm struggling with something at a higher level. So
Then when you're done, you'd like put an arrow at the top of it. Like you'd be like putting arrows everywhere. It's
Yeah,
kind
'cause
of,
otherwise you would have to like get.
yeah. Yeah.
So, so I'm struggling with something that we haven't talked much about here, but was featured in the original course that you and Nelson put on, which had to do with the fact that polynomial comonoids encode categories.
Yeah. That's what we're doing next, yeah.
Okay, so what I'm struggling with is, and it's kind of arbitrary that it's coming out now, I guess, but it just stimulated the question. So this free monad on this polynomial, it doesn't require knowledge about like the delta map and the polynomial comonoid or the
Oh, you're saying how do I get, you're
Yeah.
asking what, David, what is the map from MP to MP?
exactly.
And what is the map from Y to MP?
Exactly.
Okay, those are great questions. Yeah. Okay, so so what do you think the unit of this thing is? Which tree is it?
Why?
Just the caret, yeah, yeah. Just the caret, yeah. These things are in. The ones I've drawn so far are in this set.
Yeah.
Okay. Now, suppose that, we didn't say what the directions of this are. This is a position. This is one position. What are its directions?
Path from one
No.
subtree to another.
Okay, they're paths that get all the way up, if you want. But I would prefer you just said an open leaf.
Okay.
All the carrots, yeah.
So it.
Oh, maybe I should do something. Sorry, one quick thing. Let's suppose I had plus 2 here. Then I'm allowed to put at some of these branches 1 or 2, 1, because those are valid positions that have no branches. That would just happen automatically, right?
So the carrots represent where growth could come from.
Yes.
But
The carrots represent where growth could come from.
So they wouldn't be like the 1 or 2 endings.
Yeah, those are just dead. Yeah.
yeah.
Cut
Twig.
trimmed twigs. Yeah. Okay. So what are the leaves? The leaves of the directions here are all the open things. Okay. So now somebody gives us a tree.
Yeah.
So I go like this to indicate that it can like grow further on one part than another. Okay. So they give us a tree,
Yeah.
and then for every open branch they give us like some more tree.
Yeah. Yeah.
How in the world would we get a tree?
stick it on.
Yeah, it's just free. It's just obvious, right?
Yeah.
So that's why this is the free monad.
Yeah, and each of those points of potential future growth defines a path implicitly.
It does, yeah.
So it sort of says, yeah,
But it's a path all the way to the end.
right.
Yeah,
'Cause
you're
a
not
lot of-
allowed to stop halfway.
A lot of free constructions have this notion of paths associated.
Yeah, that's true, yeah.
And
Yeah.
so-
Yeah, so what is the free monad on, yeah, that's right, yeah.
This is just beautiful.
Yeah, it's beautiful. Okay, so let's do the free monad. Why don't you try to figure out what M0, MA for a set A, AY. Why don't you try on your paper to figure out these things? Do I want any more? And then show that MP plus A of, and then just see if you believe that. Check that. Okay, so try for like 10 minutes or five.
Doing MY before you do MAY.
Okay, MY, yeah.
I know that they're the same, but
Great. Okay. We could also do M1.
So David, a position is a tree,
A position is a tree.
and directions are the set of carroted items, potential
Yep.
areas for growth.
Yep.
Okay.
Right, so M of 0 is either Y or 0 composed MP. So we know this is Y or 0 composed something, but that's just Y. This one's Y plus 1 composed M1. So that's just Y plus 1. We can just get those ones immediately, right? Y plus, if you believe this formula. Y plus A composed something. Well, for any constant, composing with it doesn't, Y plus A. So we get all the exceptions monads as the free monads on data types. If you wanted to draw these with pictures, you would say, well, either it's the caret or it's an element of A. You draw, but then there's no directions there for more tree, so you're done. Okay, what's MY?
I'm sorry, could you see that last one?
If you wanted to draw this, draw it. You would either
Yeah.
draw the caret,
Carrot,
or you draw a
any of the
position,
elements of
an
that.
A, but it has no positions. Sorry, it has no directions.
Right, yeah.
And
it's
so you'd
just
be done. Yeah,
it's
there's
just
no
like
open
seeds of different colors,
Yeah,
or
yeah.
or the carrot.
seeds of different colors or the caret. Yep.
Yeah.
Okay, this one is Y plus Y composed MY, which is like Y plus Y plus Y plus.
Spindly paths.
It's
like
either
path
you
of
know
any length.
this thing or this thing
Yeah.
or
Yeah, yeah.
this thing
Yeah.
or yeah.
Oh.
how did you know to write, like, I did this by drawing trees.
Yeah.
I don't know how you need to write Y plus Y plus Y plus Y.
Oh right, yeah.
You
I'm
can
used
use
to
the
it.
fixed point formula and just
You
recurse.
you keep recursing. You're like it's Y plus Y composed something. Okay, let me put the next one in there. Y plus Y
You don't have any composed in there.
yeah.
If Y composed, you can just like throw
Yeah,
it.
Y plus MY. So now I know MY is Y plus MY. So then I'm like, oh, well, that is Y plus MY. Oh, wait, sorry, it's Y plus Y plus Y plus MY. And I never have to, yeah. Okay, and this one?
Similarly,
Yeah.
we'll end up
Y plus AY composed,
with y plus ay composed.
Y plus AY composed, etc.
So that will be sum.
Does anyone know?
Sum of n and naturals of a to the ny.
Yeah, from drawing trees. That seems easier.
Better.
Let's do that one. So someone comes and picks a letter A and draws a thing, and then or they do nothing, and then they pick another letter of A. Yeah, is that good? A, this thing, or A1, A to this thing. Yeah?
Yeah, sure.
Okay. So what is it?
A-lettered paths,
A-lettered
paths.
paths, but we don't really care about the path.
Yeah, I mean, it's just like spit.
A-lettered things with a single leaf at the end.
Yeah.
Okay.
Yeah.
How about is it true?
Oh, wow.
I like to,
Yeah.
yeah.
It's a list of A's,
I
yeah.
wrote it, which is gonna be the same. What can I say?
As, yeah.
I wrote it the sum
Some.
over natural numbers, because that's like the height of my tree.
Height of the tree.
And then for each node in the tree, I needed an A, so A to the capital N, Y.
Yep. Great.
I think we should practice drawing trees and do MY squared.
Well,
Oh, you're gonna.
we're gonna
Yeah, okay, good.
find two maps like this. Yeah. Okay. Can you what would be the convincing argument in your head that these two are the same? So one person draws trees that branch like P, but they're allowed to put an element of A anytime they want and stop it. Right? There's no more branches. The other draws trees that branch like P, and then at all the open leaves. Oh, sorry. Start over. This one has trees that branch like P, but they're allowed to draw an A anywhere they want. And we're looking at the constant terms of that, meaning the terms with no open leaves. So imagine a tree that branches like P, you're allowed to put an A anywhere you want, and there's no open leaves. Versus a tree that branches like P, and where every open leaf there's an A on it. Are those the same? What?
Then there's no.
Then there's no open leaves.
By
Yeah.
open leaf, you mean?
A direction, yeah. So yeah, does that make sense? Do you guys see it?
Yeah.
Like you have this P tree, it's branching any way you want. You're allowed to put an A anytime you want on it. But I want you to make sure that at the end there are no open leaves. These are the constant. When you write of 0, P of 0 is just the constant terms. They're the ones with no open leaves. For any polynomial, P of 0 is the thing where there's no directions. So I want you to give me trees that branch like P. You're allowed to put an A anywhere you want, but they have no open leaves. Well, so I have to put little A's everywhere. In this one, I branch like P, and at the top, wherever I stop, I put an A somewhere, and those are the same. Okay, so these are the same. So yesterday when Joachim said the W type, he wrote this, which would be the same thing as, or he wrote this, which would be the same thing as that. I don't know. It's not that important. It's just MP of 1 is the positions. Ah, right. He was looking for trees. Yeah. I know what's going on. Sorry. MP of 0 is called the free P algebra. I think I'm just telling you stuff that is not super important, so I think I'll stop. Let's just do these two maps, and then we'll actually move on. Okay, so what are maps from Y to a polynomial? If I have any polynomial, what's a map from Y to it?
A choice of position.
It's a choice of position. So I'm just asking for two positions in here.
Yeah.
Okay. We need to draw two positions. So somebody tell me a position in here.
Position will be caret. Just one.
Okay. We only have one more.
One.
All right, let's do
Caret
four.
and
Let's do
one.
4.
Oh.
1. Okay. Somebody else? 3, and then on the first one?
Can I do another 3?
Uh-huh. And on the first one?
1. And then 2. And then
On the first one?
3. And then
On the first
I'll
one?
close it all off.
Just dots everywhere?
Yeah.
You don't want any open leaves. Okay. Cool.
Oh, just for that 1 3 piece, actually. I meant,
Oh.
But
Okay.
And then caret 2 dot caret 2 caret 1.
Great. Anyone have another position? I'll pick one.
Yeah, that's a good one.
No, I'll just do that, actually. Okay. Okay. This one has no directions. This one has 1, 2, 3 directions. This one has no directions. This one has 1 direction.
Doesn't it have 4?
Which one? 1, 2, 3, 4.
Can
Thanks.
you remind me, for us, what the directions are?
The directions are the open leaves. The leaves, the carrots that are remaining on there.
The directions are the carrots.
Yeah.
So for constructing those trees, what causes one of them to be open? Oh, if it
Your
ends
choice.
with a carrot.
Oh, why? Yep. Yep.
Okay, so the ones that end with a carrot are the.
Directions.
Oh, I see. That notation now makes sense.
Do you guys see why I called it positions and directions instead of shapes and positions? I don't know. I feel like arrows are direction-y.
Yeah.
In dynamical systems, the directions are the ways you move.
Yeah.
Yeah.
I think it's
You
wonderful.
can call this a shape because it is a shape. It's a great name for it. And you could call these positions of the shape. But in terms of like dynamical systems, which is more the side I was looking on, it felt better to me. They're kind of the arrows.
I finally figured
Yeah.
out that we're no longer talking about what reaches the top of the tree.
Yeah. Yeah.
First of all, because the tree is infinite.
No, these are finite.
Potentially infinite. No?
All
No,
these
they-
trees,
Yes, grow arbitrarily.
they're arbitrary. They're arbitrary heights. Yep,
Arbitrary length.
yep. If p is infinitary, yes, they can be infinite. But we're only looking at these simpler cases. So what is m? What's m list, by the way? I can't stop apparently. M list. Can somebody give me a direction, a position in here?
The empty list.
Aye. Another one. M list. So I could go 4 and then 2. Sorry, 2 and then 4. 2 and what? 2.
Yeah, okay, first I pick a position of list, which is a number.
First you pick a position of list, which is a number.
Directions.
Has 2 directions.
On the first direction, I'm going to pick 3. No, I'm going to pick 7. I'm going to do that. And then I'm going to caret those all off.
Okay.
And then on the other direction, I'm going to pick 1. And then I'm going to pick 1 again. And then I'm going to pick 1 again. And then I'm going to pick 100. And then I'm going to caret those all off.
Okay. Okay, so here with this notation, you drew both a position and a direction.
I did? No.
No, you both a position and all the directions at that position.
Yep.
So under the data structure interpretation of Poly,
Yep.
what does this represent? It feels like it's
It's a list.
I have a
of
question.
lists
Do you have a
of
map from?
dots.
Yeah, it's a list. It's a list where of lists 7 lengths long, and then a list of a list of a list,
Yeah.
singleton, and then 100 length list.
Right. And any of those could be terminated with an empty list. That would be.
And any of them could be terminated with an empty list.
Yeah.
but this doesn't type check.
Why? What doesn't?
It's oh well, it's because oh wait no yeah because the list on the
Okay, can you give me a map from M list to list? List is a monad, and for any monad, there's always a map from M list, from MT to T. So apparently there's a map from M list to list because list is a monad. So apparently I can turn this position, or this, into a single list. Flatten.
But this wouldn't. When I said that this wouldn't type check, is that if you filled out those blanks with integers.
Yeah,
okay,
yep. I could flatten that into a list of integers. It
yeah,
would have 107 integers in it.
Yes, but only after you flatten. Like
Yep,
that-
that's this map. This will be, whatever the monad operation of list is, this will be the monad, will be the,
Yeah,
will be kind of like what you do. Yeah. I mean, you'll just do, yeah. So if you want to check if something's a monad in your head, just imagine drawing a tree of, like you're like, oh, is P a monad? Somebody wrote down a monad. Is that P is a monad? What is, how would I do it? Well, you could imagine drawing trees, P trees, and see if you would know how to collapse them. So that's what I did when you guys were like, what is TU? If TU is a monad, how does it look? Well, I drew a picture of like a TU tree, and then I showed you how to collapse it, right? I mean, one way to do it is just collapse a two-ary. I don't know. There's lots of ways to do it, but like, yeah. If you could imagine doing it for any shape like this instead of just two, and like we know that if T is a monad, there's a map from Y to T and T composed T to T.
Yeah.
But we also know that like there's all this associativity and stuff you might have to check. But if you can get a map from M T to T, you're probably good. T is probably a monad. Yeah.
I guess
I don't know.
what I'm a little,
Yeah.
because this notation is very suggestive of, hey, you could plug whatever integers here. You could
Yeah.
plug numbers in the
Yeah.
position of the list. But
Yeah.
actually you couldn't, because that wouldn't type check. What you need to
No,
do,
you can
what
take
this is expressing is all
Check
is
TU.
M list of int.
because
Yeah.
because
Or
you
nat.
have it's a heterogeneous list. Like the first one is just one nested, and the other one is nested 7 times.
Yep.
But it's
Three.
Aren't they typed, sorry, aren't
no.
they of type M list, which is like, that's
Yes,
the type.
yes, that is the type. But if I'm thinking of that as just one list,
This, you should not think of this as one list. This
I know,
is,
I know.
yeah.
It's like it's ways of collapsing lists that could be filled in
It's trees.
there.
yeah, these are
Yeah.
trees, yeah. Yeah,
Yeah.
yeah.
But each of the carrots could hold a value.
Oh, it will hold a value. If you put list,
Yes.
M list of naturals,
Yes.
all these will hold a value.
Yeah.
Yeah.
So what list arises as a free?
List is a free monoid. Yeah.
Oh, okay. But there's no polynomial P such that list is
M sub
the
P, no.
free- Okay.
No.
What's the question?
List is the free monoid
Yeah.
polynomial. It is not M sub something.
Yeah.
However, list of A is the free monoid on AY of 1. So like list of anything is like can be obtained with free monoids, but list as this one I find confusing actually. I'm still like, what is going on with that? So I don't know, but yeah,
So list is not
it's kind of
a
cool. Yeah,
free mono.
list is the
monad.
free monoid, the
Right.
free times monoid.
Exactly.
Free.
Yep.
There are free times monoids. That's list.
Yep.
There's a free tensor monoid. That's something or other.
Yep.
You could go figure out what it is. There's the free tri monoid.
Right.
That's this.
But it's not the free monad.
But list is not the free monad on anything.
But it can be produced by.
But list of anything can be produced with free
Exactly.
monads. Yeah.
Oh,
Sorry.
That's interesting.
That is weird. Yeah.
That's
It's interesting. Yeah. I find it a little bit disturbing for some reason. I don't.
That's what
In the
makes it
sense.
interesting.
Well,
that's-
yeah, it is interesting. Sorry, it's interesting, and I haven't I haven't figured out like what math thing that's already known is the way I'm supposed to think about this like fact.
David,
Yeah.
so M list is a tree, and then we can flatten that into a list. Is that flattening? Is that?
For any monad,
Yeah.
there's always like a way to take free monad on T to
Yeah,
T,
I think.
and it'll always use the monadness of T.
Like I think that the confusion was that because M list is not a list; it's a tree.
Yeah.
It's trees of yeah.
It's tree. So is the flattening? Is that like a topological sort of the?
I mean, I don't know if it's topological. It's yeah, left to right sort.
Seems
Yeah.
like it, right?
Yeah, depth first. I don't know. Yeah, it's the thing where you just like just
Yeah.
traverse. Yeah.
I think if you had these, like if that, imagine filling that with integers, that would not work in Haskell. But imagine closure or something, it would just give you everything in the order that they appear. And like first level of nesting, that's gonna come before any.
Oh no. I don't know.
No, it's gonna.
Like if you have-
it's gonna-
There's only one good map from M list to list.
Yeah.
Yeah, there's only one monad map from M list to
It's
list.
depth first.
Yeah, it's depth first. Yeah.
Yeah.
Yeah. Yeah, you go up and you.
You
but like you're
Actually, go.
it's like you're indexing into 0 until you hit something that's not a list. It's just an element. That goes first, and then you do that for the next one. Yeah. So like
Yeah. We probably all agree. It's
like the order from left to right in which the nodes appear. That's
Yeah.
what that should be the order.
Is there an equivalent function in the infinite case, or would it be quite different?
It's quite similar.
Okay.
I don't know. What did you ask? Is there an equivalent what?
Like if you could just arbitrary, well,
Yeah.
if it could be infinite depth.
They can be infinite depth.
Okay.
Yeah. Yeah. I think if you're into set theory, like Axel, ACZEL, non-well-founded set theory or something. If you're into set theory, which I think you are, Thomas,
Yes.
I think you might be interested in
Right, and
this
let's just create-
guy's
you just use the three.
name.
Yeah, yeah.
And yeah.
I'm sorry, so that thing you wrote down there that you can get any list of A as a free monoid, can you just help me parse the superscripts and subscripts? Is that M sub
M sub,
AY?
remember M sub AY was
Right.
list of A?
Yeah.
So if I plug in 1, I just get list A.
Literally pick a module.
Okay, so the-
I'm just look at this, and then you have this.
Okay.
Yeah.
Close,
Okay.
close.
Yeah.
Okay.
Well, yeah, but this,
And then open.
Got it.
Then
right, but it doesn't ever get, but that, it never gets
Technically,
expressed like that here either.
this
I know.
word was 6
Yeah,
and
yeah.
then that
Doesn't
one's
get
7,
expressed like that
right?
anyway.
Oh.
It was
Yeah.
it was an extremely dumb question. Like it's just
It's confusing.
if you fill in those blanks with integers and treat this as a Haskell expression, that would not check.
That doesn't, yeah, what he wrote, right. Yeah.
What did I not? What's wasn't type check?
No, everything's fine.
Everything's fine, right? Okay.
Everything's fine.
Okay.
Yeah, yeah, it's all good.
Okay.
I just have one more pretty maybe dumb question.
Yeah.
So is tree the free monad on list? Is that what-
Tree.
Yeah.
Yeah.
I don't know tree, but it's probably the free mode on the list.
Yeah,
I would
it's-
believe it.
Well, it's
it's-
like
every-
not a binary tree, but like
Yeah,
Binary
so
tree should be the free binary tree should be M2y.
Either a
Yeah.
node
Y
or a
squared.
Either a node or a list of trees.
it's a.
What's MAY to the B?
Uh,
Well, it's trees that print an A at the base and then branch like B. So if you wanted binary trees,
oh, it's a labeled.
if you want, yeah, it's a labeled tree. If you want
That's
like
cool.
Y squared, it would like label a gnat and then branch twice and then keep going.
And it would keep on labeling?
It'd be like 5, 2,
Yep.
caret, 3, caret, caret, caret.
Yep.
Would be in here. Okay.
We're gonna do
Okay. Co-free. Yeah, let's do comonoids. It's a little, yeah. Are you, do you guys want a break or are you good?
Can we take a 5-minute break?
5-minute break?
Just need to go to the-
Yeah, okay, 5-minute break. Okay. Oh, Nate's not here.
Oh, no,
Oh, you are here. Okay. Okay, I wanted to tell, so I've been saying for a while that maps into,
Are we on Comonoids?
we're going to do comonoids next.
Okay.
Maps into a trie are easier. And one way to say that is there's two interesting things. We've said one of them before. Poly PQ2, Q1. So if there's an adjoint, it means like there's different ways to calculate this. If you're trying to map into something, if you're trying to find a map and you know there's an adjoint around, then like that means there's multiple ways to think about it, right? And that can help you in different times. You can rearrange stuff and do a thing. So what if you remember PQ, maybe PQ2 is the sum over I and P of 1 of y to the q. The q is kind of upstairs, and it's upstairs there, and then p bracket I. And if you like words like con extension, then we would say that poly has all left con extensions. But if you don't like con extensions, right, so you could calculate like what is, okay, I'm going to square something, and I'm going to cube something plus 1, and I want to know the con extension of this. It's very easy to calculate. You just plug right in there. So that's kind of nice. left con extension is there. But another fact that like is, I think it's called the multi-left adjoint, is uglier to write, but very useful. And that is you choose f from P to Q. OK, here's what's going on. Remember, if you have a map from P to Q1 composed Q2, how we read it? We say we first, for every position of P, we pick a position of Q1. For every direction there, we pick a position of Q2. And for every direction there, we pick a direction of P. But the very first step was for every position of P to pick a position of Q1. So let's just put that outside. Sorry, wrong here. Let's just put our map from P1 to Q of 1 on the outside. And then what's a multi-left adjoint is that you can, I think that's what it's called, is that you can then form like that. And what this says is that we can do the rest of the calculation. We can somehow move the rest of Q1 over to P. So what is that weird thing? P, so given F, a map on positions from P of 1 to Q of 1, we'll define P frown over F. You could put smile, but then F kind of sits in the smile. It's weird. And also, the reason for this is it kind of like brings Q-ish stuff downstairs, but whatever. OK, you can pick a different notation if you want. This is the sum over I in P of 1 of Q bracket F of I, y to the P bracket I. So it almost looks like P. In terms of positions and directions, it's all there, but you put like some new positions there. So let's do P id P. What is P id P? It's sum, right? I in P1. Q? Who's Q? Who's Q? Who's Q?
Q is P, so P of y over y to
Yeah. Great. So it's kind of like sy to the s lots of times. P1 y to the P1, P2 plus P2 y to the P2 plus. Like it's, you take all the positions in P and you do sy to the s for their directions. Right, so like y to the s would be sy to the s. But I denote this thing P star. And the reason is what is P star of 1? Well, I don't know if you'll think this is a reason, but what is P star of 1?
is P of like summation I P of 1 P of I.
Yeah.
So it's all
It's all the directions. Yep. And there's a map to P of 1. And this is what Joachim denotes a polynomial as. P star of 1 mapping to P of 1. That's the bundle.
That's the E and F?
That's the E and B, yeah.
E and B?
Mm-hmm. Yeah. So, yeah.
So when I say it's all the directions, it's you're taking the directions at each position and smooshing them together.
And adding them directions. All adding them together. Yeah. So, okay. Yeah.
Nate has a question.
Yes.
Yeah, I somehow got, again, horribly lost.
Sorry,
in
yeah.
a maze of little corridors all looking alike.
I'm
okay.
about to try to move into comonoids.
Right,
And then later bicomodules.
yeah. So maybe
and
we should-
sometimes we have maps in comonoids and bicomonoids. We often have maps from
Yeah.
a thing into a composite. And so it is useful to know a couple facts about maps into composites.
Okay.
We already know they're easy in a bunch of different ways. They're
Yep.
easier than maps out of composites.
Yep.
But the fact that they're adjoints makes that a little bit clearer.
And so you've
And
given
so-
another way to view them here.
Yeah. This one gave us lenses yesterday.
Yes.
We were all
Yes.
interested in like people
Yes.
like to write STAB and stuff like that.
That's right.
Yeah. Okay. But now we might want to use this other one, this weird frowny thing, which says if you know the map, if you want to map from P to Q1 plus compose Q2, first tell me what it does on the very first part of positions, from P to Q1, just on positions. So choose that, and then choose a polymap for the rest of the way. Like it says, once you've chosen that, I can do a thing where I like move the directions of Q over into my P, and that, yeah, maybe we should try. Maybe we should do an example. So, okay.
Oh, that's funky.
Can you give me a map from P star to P? I told you there's this map, P star of 1 to P of 1. But in fact, there's a map from P star to P. What would it be? So I'm looking for this, and I deduce that it's enough to look for what? Let's see. That's weird. Yeah. Well, this yeah, I know, let's see. This is sum over I in P of 1 of Pi y to the Pi.
Yep.
And I need a map from that to sum over I in P of 1 of y to the Pi.
Yep. Yep.
Pretty easy, I think.
Pretty easy.
Yeah. Take the position
Yep.
and the direction, toss the direction in the
Exactly.
trash, have the position, give it a direction,
Yep.
take the direction. Okay.
Yep.
Wait, is there another one where
Yeah, there is another one.
there's another one where you put it, you ignore
Yeah.
the inputs that you get, and then you use
Yeah,
their
there is another one. Yeah. Yes, there's two. There are two of these. But, and they're both, yeah, they're both great. Yeah. Okay. But we know this is the same thing as a map from P id P to P. That's this. So we know we're over here where F is id. And so that's the same thing as a map from P to P composed P. Why am I writing all this? Why am I writing all this? Okay, I guess I'm asking what map is this? Maybe that's what I'm going to ask. What map is this? Apparently map P star to P gives me a map from P to P composed P. Which one is it? For any polynomial in the world, there's a map from P to P composed P. And not only that, it's actually like, for some reason, surprisingly fundamental. So I think this is a kind of weird thing. So where does it send I? I don't know. I don't know if this is useful or not. But where does it send I? To itself. How do we know that? Because we said we were going to use id for the first part. We also know because where else could it go? But yeah, I. And then for every direction there,
Yeah.
let's see. I'll draw it with polyboxes. So we have P. We take our I. We send it to I. Given a direction, I need a position.
I.
Yeah. That's because this I went there. Okay.
They all collapse. You're
And then
saying?
given
Yeah.
D prime,
Yeah. D prime.
should I go to D prime or D? Well,
Those are the two that exist.
those are the two. Max said to use, we could use D, but the one that gives you this is D prime, the new one.
It's kind of like going to the final location, the final
Yeah,
branch,
the last
end
one,
of
the
final
last thing.
branch at the top.
Yeah, there's all these positions in P, and each one has a bunch of directions.
Yeah.
And it's kind of like where is my cursor sitting?
Yeah.
And you can just keep moving it around, and it just tells you where it ended up.
Yeah.
Yeah. Okay. It turns out that the two that Max thought of, one was going to end up being domain, and one's going to end up being codomain for a category. But we're not there yet. So it turns out what I'm saying is that P star is a tricomonoid.
Yeah.
And it's a bunch of sy to the s's, and sy to the s is a tricomonoid. And we're going to talk about all that stuff soon and how they're categories and stuff. So our next job is to talk about tricomonoids.
So you really call this frown?
Yeah, I call it frown, yeah.
Okay. And there's a
Backslash,
character for it?
yeah, backslash frown
Okay.
in LaTeX.
If it were G, it would be a ground.
What?
If it were G, it would be a ground.
What G? Oh, I see. Okay. Okay, all right, so yeah, I hope this is helpful. I thought it might be helpful when I was thinking earlier today how to talk about this stuff. But it exists and it's interesting. So let's talk about tricomonoids. So if you're in a monoidal category, you really ought to ask what are the monoids and comonoids, no matter what monoidal category you have, if you're trying to explore it and learn more about it. And so poly with tri is a monoidal category, so it's interesting to ask what the monoids and comonoids for it are. And the monoids are monads. And we did a bunch of them on that board over there. Lott is a monad. List is a monad. But now we're into tricomonoids, which are comonads. A tricomonoid is a C in poly, a map from C to Y, that we'll call epsilon, and a map from C to C composed C, which we'll call delta. This one we'll denote it epsilon and delta. This one could be called co-unit, and this one is called co-multiplication. And as usual, they satisfy these laws. If you start with a C, it's isomorphic to C composed Y and to Y composed C. And each of, what did I do? It goes to C composed C, and that goes to, what? Okay, I don't know. C, I don't know why I feel confused that my diagram feels different today than it did yesterday. But Y composed C, and that's isomorphic to that, and that's that, and that's that, and that's that. C tri epsilon, epsilon tri C, C to C tri C to C tri C tri C, C tri C, C, delta, delta, C tri delta, and delta tri C. And for those of you who like these pictures, it's like this. And this.
David, a
Yep.
question from way before.
Yeah.
Why is the frown there? Why is it a shriek? Under-
Oh, there's only one map on positions from this of one to this of one.
Yeah, but on directions there's many.
This symbol here, this F, labels a map on positions.
Ah, right, yes.
Thanks. Good question. Okay, so somebody says I've got a comonoid in poly, and your job is to tell them why it's interesting. That's what happens. Like if you're exploring you have a monoidal category and you're exploring you're exploring the monoidal category, you ask what the monoids and comonoids are, but like just knowing the definition doesn't help you that much. You have to like try some examples and see if you can figure out why this thing matters or what it would matter for. And it's not always easy. So, yeah. Yeah, so Amun and Ustalu, I mean, I don't know very many references because I just like work on things myself because I'm just not a very good reader. So it's pretty sad how many references I've given compared to how many Joachim can give. But I asked Joachim at some point, what are the comonoids in Poly? And he said, go look at this talk by Richard Garner. And Richard Garner said that these guys, Daniel Amun and Tarmo Ustalu, had proven that comonoids in Poly are exactly categories. So I happen to know that. Comonoids are categories. Small categories. What did you say?
I have a question. Why do you not emphasize that they are small categories?
Instead of saying categories?
Huh?
I mean, small means like the real numbers, like the size of this thing is bigger than, I mean, small set does not mean finite.
I know, but it's
It just means not a proper class or something. It's
like elsewhere I see people
emphasize smallness.
smallness a lot, yeah.
So I think it's
You don't get
because
set from this.
for any size set, yeah, smallness,
Like
a lot of times people are exploring and they do weird stuff. And when you let yourself repeat the same construction infinitely many times, like things that's a fun thing to do. But like for smallness or something, like you kind of, if you just say, you talk about small categories, then large, then very large, I don't mind. Very, very large, fine. Just don't do it infinitely many times or something. I don't know. So like any size set you want, even if you thought it was huge before, it's small from another point of view. Just don't keep iterating things that like grow your size.
Yeah.
At least that's how I think about it.
Yeah, I mean, I only asked because it's like first time I saw this, I was like, wait, how can set or
Yeah.
the functor category be
Yeah.
a
Set
comonoid in
small as long as you like look at sets inside of a universe that is, big or something. You just say, I've fixed some inaccessible cardinal, or you say some incantation about, from somebody who knows what they're talking about, and they've solved the problem of size for you, and they've given you like all the things you want. You can take power sets in there, you can take exponentials in there. They've guaranteed that all the constructions of set theory work.
Of that set theory.
In that set theory, yeah.
So it's like there's some version of set where you threw out a bunch of stuff that is like frivolous. That is a comonoid in
What?
in Poly.
Yeah, if you take finite sets, for example, that will be a comonoid in Poly.
Uh-huh.
The category of finite sets.
The category of finite sets is a comonoid in Poly.
Poly, yeah. Or like.
Sorry. Yeah.
So like. The category. Yeah, roughly speaking, the category. What I'm allowed to say is the category of finite sets is essentially a comonoid in Poly.
Essentially.
Yeah, it's equivalent to a comonoid in Poly.
Okay.
Yeah. Okay. In other words, there might be like proper class of finite sets, but it's so weird because basically it's like, well, that's a finite set, and like that's a finite set. You're allowed to put any like thing you want as a one-element set, and you just there's a proper class of one-element sets or something, but that's like dumb.
Right.
If you agree that's dumb, then you can agree that that the category of finite sets is a comonoid in Poly. Okay. Okay. Right. Okay. So, I guess let's just launch into it. Let C be a category. I guess small. for each like object of C, let's write C bracket C to be the coproduct over all C prime of HOM in C, from C to C prime. All outgoing or emanating arrows from C. Okay? So C bracket C are all the directions out of C. Like you're at this object C, and you look out in your field of view, it's like, where do you want to go? Or which direction do you want to go? And then you're going, and then at some point someone can tell you the codomain later. So we have this map from like C compose C to ob C called COD. Does everyone agree there's something called COD? Codomain of an arrow. Okay, and this would send like C prime F. If I had an object and a morphism, it would send it to C prime. Okay. So this is all the outgoing arrows, and if we want to, we can always ask for their codomain. For any one of them, we can ask for its codomain. Okay. So how do we form a map from, okay, let C be C colon equals sum over C in ob C, y to the C bracket C. These are all capitals. Is this a polynomial? As long as this is a set, yeah. Okay, this is a polynomial, and I claim that we will be able to find a map from C to Y and a map from C to C compose C, and that they'll satisfy the equations that we need. So what is the map from C to Y? A map from C to Y is a way of picking for each position in C a direction there, right? Okay, so for every object in script C, we need an outgoing arrow, just by virtue of this thing being a category. So what is it? What is epsilon sharp sub C? Remember, yeah, it's ID. So we have this C. We have this object, and we need a map to 1, 1. We need like that sort of thing. Do you agree? Y, Y. Okay. So we pick what? IDC? Yeah. And then we need a map that takes an object of C, ob C, and gives us an object of C, and then for every morphism, an object of C, and for every morphism, a morphism of C. Okay, so given an object of C, what object of C do you give me? I'll give you an object of C. What object of C do you give me?
C.
Okay, great. I'll give you a morphism F emanating from C. What object of C do you give me?
Codomain.
Cod F. Okay, I'll give you a morphism emanating from that. A morphism emanating from that, from Cod G, from Cod F. What morphism do you give me?
F compose G.
Yeah. Does this make sense?
What is that symbol after the E to the left? On the old equation.
Here?
Yeah, the
Epsilon sharp C. I wrote a map like this takes for every position of this, a position of this, and for every direction there, of which there's one. okay, it turns out that the unit okay, suppose somebody stuck on the unit here. They took, so these are the things we need. And then we want to, let's say we want to check some stuff. So we take this thing and we check the two laws. So we check this, that if we did what they say for delta, and then we did the epsilon thing on either side, that the resulting thing from here to here would be identity. We would see the same symbols here and here, and the same symbols here and here. So let's do that. Okay, we're expecting that if we run delta and then epsilon on either side, that the symbol here, we're expecting to find that there. And we're expecting to find this symbol here, whatever it might be. That's what we're expecting. And, and we're expecting to find whatever's here, there. And whatever's here, there. That's the expectation. Because we wanted this to be a comonoid. And that's what comonoids do, is here, it's these things. This little circle-y thing here turns out to be this little circle-y thing here. Okay, so let's try it. Okay, so what symbol should I put here? Well, this is ob-C. So we're supposed to pick an object. C. Okay. Where do we say to send it? We're going to follow these two. Yep. So C, and then what do we put here? What? Nope. Not just any F. We're supposed to use this. Identity C.
Yeah. Epsilon.
Okay. Now I need to put something here.
C.
No, I need cod of id,
Yeah.
which is C. Okay. Yeah. So cod of the identity is C.
Yeah.
Oh, I expected that. Okay, great. And then given an F here, I'm expecting to see F there, but instead I accidentally got identity composed F. Great. F equals identity composed F. Similarly here, I start with C. What do I get there? I'm expecting to see a C. But unfortunately, I have to follow this pattern. Luckily, it works. Okay, great. F here.
Codomain of F.
Cod F here.
ID.
Id on cod F. Whatever cod F might have been, this is id of it.
Yeah.
And now I'm supposed to put the composite of F and id cod F.
Yeah. F.
And that's F. So I expected that, and we got it. And then you'd have to do it for the, should we do the other one too, or do you believe it? The associativity? Maybe we should do it.
But I think it's kind of cool.
Yeah, it's kind of cool. So let's just do it. So we do this, and then we do this, this. Sorry, the board's getting kind of cluttered. Maybe I should just use a new board. Seems polite. Okay. So for associativity, it's not like, it's kind of the same story, but it's worth doing because it comes up in other settings like bicomodules. If you want a highbrow reason that comonoids are categories and bicomodules are parametric right adjoints, Richard Garner wrote a note that I think he can make public, although he sent it to me. And it's very concise and pretty if you like high, NLab style category theory. Okay, so let's do associativity. Associativity says that if we run delta and then we run delta again on the bottom, it's the same thing as running delta. So I'm just reading, I'm kind of reading this diagram here. It's just that circles, I hope it's clear.
Rigmarole.
I mean, these are kind of pretty diagrams. When you draw them on a computer instead of like this, they look, these are very nice, kind of, right? Yeah. Okay. Okay, so here we go. Delta, delta, id, delta, id. Okay, so what do we put here? 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 Here?
Just some F.
F. Here? Cod F. Here? Any old G, yep, G. Here?
F composed.
F composed G, here?
Cod F.
Cod F composed G. Sorry, it's tiny. Cod F composed G. Here? Cod F composed G.
You can just draw a fish.
Here? Just an arbitrary H. Here? Nope. This is id. This is me copying all the way down.
Yeah.
Yeah. In some sense, you don't need to draw this one even. You could just use this one. It's just you kind of start to forget where you are.
Yeah.
Okay, so this is H, and then here? I'm supposed to follow delta on this, right? What?
F composed G,
Yeah.
and then followed by H.
Okay. Okay, great. And so now we do C, 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 right?
Yeah.
And then someone gives us we copy, we give this, we're supposed to fill in our part of the spreadsheet
Yeah. Yeah.
the same way.
Yeah.
And we're going to check that these things are the same. Sorry, we need to check that this and this thing and this thing, this thing and this thing and this thing and this thing are the same. Okay, that's our goal. Okay. Okay, oh, we checked out one, that's good. Next.
F.
Okay, is it bad that these don't agree?
No, it's not.
That's fine.
No.
As long as the composite, yeah,
Yeah. There's
Yeah.
different context for them.
yeah, yeah. They're just different.
Different calculations.
Yeah, that's right. Okay, here, cod F. Here, this one we do care about, cod F. Check. Okay. Then we're supposed to put a G.
Yeah.
This one is what?
FG.
Y cod FG?
F then G.
Y cod F then G? We're supposed to just follow delta.
Just G.
Cod G. Uh-oh. And then H, we have to check some stuff later because this was not obvious. So this one is what?
G composed F.
G-
G composed H.
And this one?
And then it's F, then G composed H.
Okay, so this one's okay, right?
Yeah.
Because of the associative law.
Yeah.
So now we need to just check that if we had this C and this F came off it and it went to cod F, we don't know what that's called, but we had a G coming off that
Yeah.
and we went to cod G, we need that to be cod of F composed G.
Right.
But it is cod of F composed G. Great.
It's just so
Yeah, it's pretty surprising to some people. Some people, when they heard about it, they're like, yeah, well,
kinda makes
isn't it
sense.
obvious that comonoids and poly are categories? And I'm like, you are good at math.
It's like, well, it's like
No, this is people, it's Mark Weber. And I told him, and he's like, well, isn't that kind of obvious? I guess it's because he knows this stuff very, very well. Yeah. Is it obvious?
Well, it makes sense. It's like the positions are positions, and like the
Yeah.
monoid stuff is like the exact stuff that would be like making directions behave like arrows in a category.
Yeah.
It does like it kind of like feels like the right thing. I don't know.
Okay, I'm glad. Yeah, it wasn't obvious to me. Yeah. So what we could do is we could go the other way, but we have only 5 minutes. and then lunch. So let me just ask, like, let's say you have this category here. Let's say that's C. What is the carrier polynomial?
So that, oh, that's
There's a category. It's got 2 objects and 4 morphisms.
y cubed plus y.
Y cubed plus y.
Because the y cubed is from the identity and the 2 outgoing arrows on the
Yep.
left. and
We
then-
could, if we were being like kind of more polite to ourselves or something, we could say, if this was E and this was V,
Yeah.
we could say this was Y to the E, like identity on E, source target,
Yeah.
plus Y to the V, as in identity on V.
I love that notation, by the way. I think that's awesome.
Which one, this notation?
Yeah. I mean, I think it's really helpful when you do it.
Cool. In fact, since this, we could, okay, here's the thing. If you've got a set, 1 times A is A. So like Bob times A is A. So I can like multiply this with any 1-element set and not change the polynomial.
To label it.
And I can also not draw time symbols because I said we can just concatenate things. So I could say this is E like that plus V y to the V. So this lets you know this object, these are the 2 objects. These are the outgoing morphisms of this one, and these are the outgoing morphisms of that one. Okay. What is the map from this to X to Y? Where does it send? Well, for every position, I need to pick a direction.
Yeah.
It's kind of already in there. Yeah.
The identity.
You pick the one.
denoted with
You pick the identity, which happens to be the one that sends E to E. Yeah. V to V. Okay. I mean, let's just map from this to it compose itself, and then go to lunch. I hope we can say it out loud. I mean, there's a lot of activity to write that out, to say what the map we're about to try to say it, is to give all of the codomain and composition data of this category. There's 4 morphisms in this category, so there's 4 things to take codomains of.
Could you?
And there's like 1, 2, 3, 4, 5. I think there's at least 6 things to take compositions of. I think there's around 6. Identity with source, identity with target. So to give a map like this is to give like kind of like maybe 10 pieces of data-ish. So it's not like you can just like, to go through it would take us some effort to write to 10 things. But let's try.
A tree notation might be manageable there, right? You can use some good space.
Maybe. How big is this tree? It's y cubed plus y.
Yeah. And then so it's got
Composed
3
y
branches
cubed
out of
plus y.
And then you're gonna get those 9 branches up there.
So there's like
Yeah.
y to the, yeah.
Yeah.
It's not a bad idea. It's an interesting idea. Make me want to, okay.
You
We
could
could,
color it and enjoy a thing of delight.
I suppose we could enjoy a thing of delight.
So you could make the one on the left be,
Oops, one.
sort of
This one's called V, this one's called E, this one's like E, this one's source, and this one's target.
the tree arboreal.
And then there's
target.
like,
Yeah.
1, 2, 3, 1, 2, 3, 1, 2, 3. I mean, there's so many of these trees is the problem.
Yeah, there's a lot.
There's a lot. How many are there? Can someone tell me before I start this? 3 to the 3 is 27. So you've got me writing 27 plus trees here. Well, let's just say what it does on positions. So
Yeah.
this is going to a height 2 tree. Which one? Okay, I need to
Oh.
send this position, E,
Yeah.
to a
Yeah.
position here. What
Yeah.
position do I send it to? Well, we're supposed to, we're doing delta right now.
Well,
So we're supposed to pick E. Okay, so we'll pick E at the bottom. And then what do I put for source? What tree? I mean, for E, I mean. Well, I'm supposed to follow delta.
Right.
Delta says that whatever the person picks
Right.
for their direction, you're supposed to give them cod. So what is this one?
it's gonna be E, but
Yeah. Okay, for this one, source?
this.
No, I'm supposed to take cod here.
Oh, yeah, V. It's
Yeah.
gonna be V, which is gonna be the
And this one,
V again. Yeah.
target. Okay,
Therefore,
and for
that's
this one?
branch, because V is one branch. Yeah.
This one?
V is
And then for the identity, what do I put here? V, yep. Okay. So this is the map on positions. And now I need a map on directions. Where do I send this one? Obvious.
it's the end one.
So this is E,
Yeah, the
source,
final
target. Okay, so where do I send E back here?
E,
Where do I send source?
source,
Where do I send target?
target.
Where do I send the thing above source?
Says,
So this is identity.
yeah,
Where do I send source identity?
source,
Where do I send target identity?
target.
Yeah, I'm composing. Yeah.
You're composing.
Yeah, I told myself I would be composing
Yeah.
here
Yeah.
in that other board. Yep, and that's it.
You
Yep.
could write the dot.
So we wrote all of the codomains and all of the composites were in there. Yeah.
Yeah.
Sorry to override you there. Okay, let's end.